Hello everyone, welcome to my class. In today's class, we learn approximations for definite integration. So let me start the class right away. First, quick preview. Sometimes it's hard or even impossible to find the exact value of a definite integral. In such case, we need to find approximate values of the definite integrals. Recall that we already know one such method, Riemann sum approximations. In Calculus 1, the definite integral is defined as a limit of the Riemann sums. So any Riemann sum could be used as an approximation to the integrals. We can use either left Riemann sums or right Riemann sums or midpoint Riemann sums. Note that we use n rectangles to approximate the net area under the graph of functions and bounded between two x values. So our definite integral is given on the left side, is a to b fx dx, and I use approximations right Riemann sum, which is Rn here. So Rn equals to, we sub the intervals a, b into n many partitions, and we draw our rectangles, and in the rectangles we pick a right end point and we evaluate the function at the right end point. That gives us the height of the rectangles, and we multiply by the width, and we find the area of each rectangle, and we add them up. So which is here, delta x is the width of each rectangle, where delta x is defined as b minus a over n. N is that many partitions, and fx1, the fx1 is the height of the rectangle at point x1. And for the second rectangle, the height is fx2, and so on. So that means fx1 times delta x plus fx2 times delta x plus dot 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 plus fxn times delta x. So these all are the areas of the tiny rectangles. And then we add them all. And in the abbreviations form, we write summations using index, the giant sigma notations of fxi delta x, where I runs from 1 to n. And let me talk about midpoint Riemann sum here. So if each of these xi's, maybe here, if each of these xi's are the midpoint of our subintervals xi minus 1 xi, then the Riemann sum will be midpoint Riemann sum. Okay, so let me scroll down. So here, midpoint rule, if xi means this point, x1, x2, dot 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 xn, are chosen to be the midpoint of the interval xi minus 1 xi, and we write the midpoint as the xi minus 1 plus xi over 2. So here, when I is 1, so that's the x0 plus x1 over 2. That gives me x0, x2, if I is 2, then x1 plus x2 over 2, and so on. Then this definite integral a to b fx dx is approximated by, so I use mn, so m stands for midpoint Riemann sum, so mn, and many rectangles we are using, is delta x, and fx1 bar, we use xi bar for the midpoint, just a notation, and plus fx2 bar dot 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 plus fxi bar, so this should be n here, fxn bar, and this is the certain notations. And now in this sections we learn two other approximations for the definite integrals. Let me scroll down. One is a trapezoidal rule, another one is a Simpsons rule. So let me talk first the trapezoidal rule. So in trapezoidal rule, we use n trapezoids to approximate the net area under the graph of the functions and bounded between two x values. So the f is a function here. I just pick some random functions. It's defined over the interval a, b, and we chop the AB into n many partitions, just like in the Riemann sums. So the first point is x0, which is same as A, then x1, then x2, x3, dot dot dot, xn minus 1, xn is same as B, and the width, each of the width is delta x, which we define as B minus A over N, just like here. And this times we are doing the trapezoid. So trapezoid has the two sides parallel here, and the area of the trapezoid is 1/2 sum of the parallel side times the width. So then here we construct the first trapezoid, then the second trapezoid, third trapezoid, dot dot dot, up to n many trapezoid, and find the area of the first trapezoid. Just like in a Riemann sum, we find the area of the first rectangle, then the area of the second rectangle, then dot dot dot, area of the nth rectangle, and we add them all. That is the idea. So now here you are finding the area of trapezoid. So here is the first trapezoid, delta x is the width, then 1/2 is from the formula, and the parallel side is the height at x0 and height at x1, so which is fx0, which is fx1. So this gives me the area of the first trapezoid. Similarly, area of the second trapezoid, let me scroll down, that's better. So here delta x, this width is delta x over 2, that 2 comes from the formula, and then the sum of the parallel side, f of x1 plus fx2, and so on, dot dot dot. The last trapezoid area is 1/2 times delta x, f of xn minus 1 plus f of xn. And to find the total area of the trapezoid, let's add them all. So let me scroll down. So hence adding all these results together is the trapezoid sum approximations. So we denote trapezoid by Tn. So a to b fx dx is approximated by Tn equals to delta x over 2 fx0 plus 2 times fx1 plus 2 times fx2 plus dot 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 plus fxn. It turns out to be the average of left Riemann sum and right Riemann sums. Great. Next, let's talk about Simpsons rule. So maybe one more point here in the trapezoid sum rule. There are 2's here. So first one has no 2's and the last term has no 2's, but all other remaining terms in the middle have the 2's as a coefficient. So keep in mind. Great. Now let's talk about Simpsons rule. In this approximation, we take the intervals in pairs. That is why we need n even numbers of partitions, else this rule cannot be used. Draw a parabola and let P0, P1, dot dot dot, P1 are the corresponding points on the curve. So here is our function is this f, and again same as before, we partitions the AB intervals into n many partitions. So first point is x0, then second point is x1, then dot dot dot, dot dot dot, xn is same as the last point b, and the P0, P1, P2, dot dot dot, Pn are the corresponding point on the curve. And in this case, we take intervals in pair. So first, these two intervals, x0 to x1 is one interval, x1 to x2 is another interval. So first we take these two intervals. In a typical parabola, we take a parabola, passes through 3 consecutive points. So the first parabola is passing through P0, P1, and P2. And the second parabola, P2, P3, P4, passes through these 3 points. So we take a point in pair. So two intervals have 3 points. 1 point is common. Then it turns out that we find the area below this parabola these times. Below the parabola, this is the first parabola, this will be second parabola, dot dot dot, and we have an nth parabola. So it turns out that the area of the first parabola through P0, P1, P2 is delta x over 3 the height as x0 plus 4 times height as x1 plus height at x2. So here I did not derive the formula, it's given in the book. I just gave you the formula here. Similarly, area under the second parabola, which passes through P2, P3 and P4, is delta x over 3 fx2 4 times fx3 plus fx4. Keep in mind that our x2 point is, or this P2 point is, lies in this first parabola as well as second parabola. So that's why in our sum later we are adding this fx to fx2. Correct. And similarly, area of the last parabola through Pn minus 2, Pn minus 1 and Pn will be delta x over 3, same pattern, f of xn minus 2. Middle one is a 4 times fx minus 1 and plus the last one is f of xn. Correct. Hence, adding all these results together yield the Simpson's sum approximations. So we denote Simpson's sum by Sn, just like Riemann sum by Rn, trapezoid sum by Tn, now Simpson's for Sn. So delta x over 3 is a common, then the other terms we are adding here, fx0 plus 4fx1, and plus I'm adding this 2 here, so 2 times fx2, dot dot dot, last is fx1. So note the pattern of the coefficient alternates between 4 and 2's. 4, 2, 4, 2, dot dot dot, 4, 2, and ends in 4, and then 1. The first one, and then the first term and the last term have coefficients 1. Okay? Now let's do some example. So example 1, approximate the definite integrals of 1 over x from 1 to 2 by taking n equals to 10 partitions using trapezoidal rule, Simpsons rule and midpoint rule. Great. Let me scroll down. So first, trapezoidal rule. Here is a formula. So trapezoidal rule equals to, I need to find out the width, delta x, then x0 is the left end point, which is 1, and then I need to find x1, x2, dot dot xn minus 1. Xn will be the right end point, which is 2, and x1, x2, dot xn minus 1. These points we can find by adding the delta x on x0. So here delta x is b minus a over n, that's the formula. So 2 minus 1 over 10, so 1/10, which is 0.1. So the x0 is 1, then x1 is 1 plus 0.1, x2 is 1 plus 2 times 0.1, or x1 point plus 0.1, and so on, which I wrote down here. Then next I need to find out the height at each of these points. So f of x0, my function is 1 over x. My function is 1 over x, so 1 over 1. fx1 is 1 over 1.1. fx2 is 1 over 1.2. Dot dot dot, dot dot dot. fx10 is 1 over 2. I hope this computation makes sense to you all here. Hence, our trapezoidal rule is this one. A to b is 1 to 2. Function is 1 over x, approximated by Tn in my general formula, but I'm taking n equals to 10, so T10. Then delta x over 2, let me scroll down. So delta x is 0.1 over 2, and f of x0, fx1, dot dot dot, fxn, f of x10. And by the way, besides the first and the last terms, we need to multiply by 2. That's the coefficient in my formula. 2, 2, dot 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 2. And then using the calculator, we ended up this number at 0.693771. So the area of the function 1 over x from 1 to 2 approximated by trapezoidal rule is 0.693771. And I think everybody knows the graph of 1 over x, right? This is the, you draw this the plane, x-axis and the y-axis, and then the 1 over x goes from this way, right? Right? Great. Similarly, let's move on. Let's use Simpsons rule. So the Simpson rule is given here, which is same as we discussed before. Then we are taking n equals to 10. So delta x equals to b minus a over n. That means 2 minus 1 over 10. Again 0.1. Then by Simpson's rule, the definite integrals 1 to 2 of 1 over x is approximated by s10. So this is delta x over 3. So delta x is 0.1. 3 is from formula. Then fx0, 4 times fx1 plus 2 times fx2 plus 4 times fx3, so on. And the last one is f of xn, which is f of fxn, which is 1 over 2. Great. Again, using calculator, we have this approximations 0.693150, which is, let's see, we're almost close, right? Yeah, up to 3 decimal exact number, then 771,150. Okay, now let's move on. Let's do midpoint Riemann sum. So here is a formula. So now this time, so I need to find out the midpoint. Okay, so here is a m10, n equals to 10, delta x equals to again 0.1. Note our xi bars is xi minus 1 plus xi over 2. So the x1 bar, first midpoint is midpoint between 1 and 1.1. The second midpoint is between 1.1 and 1.2, and so on. So I computed the midpoint here. And then just the routine computations, then given definite integrals 1 to 2, 1 over x, dx approximated by m10, m stands for midpoint Riemann sums. So delta x, so 0.1, f of x1 bar, f of 1.0.05, f of x2 bar, so f of 1.15, and so on. Then using calculator, we end up 0.692835. Let's see, is that up to how many decimal places we are close to the previous approximations. I think 69, yep, 69 only up to 2 decimal places. So I don't know which one is the better approximations, right? So now let's take that one aside. What's the exact value of this definite integrals? We are using fundamental theorem of calculus. The definite integral of 1 over x dx, x limit to 1 to 2. Integral of 1 over x is simply natural log of x. Put value 1 to 2. So ln 2 minus ln 1. We know ln 1 is 0. And ln 2, using calculator, ln 2 is 0.693147. So this is the exact value. But by taking n equals to 10 partitions, this is the midpoint approximations to this exact value. So we are 0.693147, 0.692835. Similarly, by Simpson rule gives me 0.693150. Similarly, the trapezoid rule gives me, by taking n equals to 10 partitions, 0.693771. And as I mentioned earlier, the definite integral is the limit of the Riemann sums. So now to find the exact area, I need to take the limit here. That means I need to take this n goes to infinity. Then that gives me the exact area under the graph 1 over x by these previous methods. Awesome. I hope it makes sense to you all. So I have one short observations here. So the integrals, the definite integrals of radical x cubed minus 1, x equals to 1 to 2, the exact area turns out to be approximately 1.51593. But by using trapezoid rule, taking n equals 10 partitions, gives me this number, 1.506361. And using Simpsons rule, it gives me 1.511519. Great. Similarly, that's the example I wrote earlier, e to the x squared from 0 to 1. This area turns out to be 1.46265. And using Simpson's rule, by taking n equals to only 10 partitions, we will get 1.462681. And we know the larger the n, better the approximations. But here that we are only getting an idea how this approximation method works. So I hope it makes sense to you all. So now this ends this section, so short and sweet. Next times we'll learn improper integral in our next class. Thank you.